everyone. In today's lecture, we'll be discussing how we can come up the quasi-sliding mode control. Because of this technique, we can reduce the chattering in the control. And also we'll have combined backstepping sliding mode control. Backstepping part already we have done, and how we can combine with the sliding mode control. And the whole concept of backstepping sliding mode control, how we can apply for the aircraft system, we'll discuss in detail. Let's set up the problems on which we'll be designing these controls. Let us consider the linearized model of an aircraft. A linearized, it is, we can, for simplicity, the linearized model of the longitudinal motion of an aircraft. I can write theta dot equal to q and q dot equal to a theta plus a q plus a u. So here, this a theta, a q, a u are the stability derivatives. So let me define these parameters here. Theta is the pitch angle. And how we can design this quasi-sliding mode control for this system, we'll discuss in detail. Q equal to, this is basically pitch rate. And U is the elevated deflection. And A theta, AQ, and AU are the stability derivatives. So here, yeah. So let me go through detail of this stability derivative parameter, because these are very important things for understanding the dynamics here. In the context of aircraft pitch dynamics, a theta basically represents a term associated with pitch angles effect on the moment equation. It is basically, we can also write, which often linked to the static stability derivatives, Cm alpha. Here Cm alpha represents how the angle of attack affects the pitching moment. And here the expression we can write a theta, this is Q infinity is C bar Cm alpha I, Y. So the terminologies already have explained multiple times in different examples. So in this term, this a theta helps maintain pitch stability when disturbed from steady flight path. Yeah. Similarly, we'll go to the next term, AQ. So I hope it is clear how the A theta is significant in this longitudinal motion. Now, A theta, AQ is the pitch damping derivative CMQ, uh, representing how pitch rate affects the pitching moment. So we can write AQ equal to Q infinity is C bar CMQ divided by IY. Similarly, CM delta E, that is pitch control effectiveness derivative. We can denote as CM delta E equal to dou CM dou delta E. So here the value of CM delta E means that small changes in delta E produces larger changes in the pitching moment, and which gives the, we can write, small change in delta E produce larger changes in pitching moment giving the elevator greater authority over pitch control. Okay. This is the desirable for effective pitch response and stability control. If now for this example, what you are taking here, we consider for the above. Let me define the equation. Equation 1. For equation 1, we consider the values of a theta, AQ, and AU are to be a theta equal to minus 0.8, AQ minus 0.3, and AU 0.5. Here, because as you have mentioned, the sliding mode control also sometimes called robust control. So here we are going to add some disturbance to the equation 1 to the dynamics. So here, let us add disturbance term dt to the pitch dynamics. So here, the structure of the disturbance, we have considered t equal to 0.1 sine 0.5 t. So 0.1 is the magnitude of the oscillation and 0.5 is the frequency. And also we are considering the initial condition for the state. Consider the initial conditions of the states. So here we are having two states, theta and q. So theta naught we are taking as 0.3 radian and q naught we are taking 0. So we have to design the control u such that theta and q are controlled or stabilized. So for this purpose, we need to choose the sliding surface. So let us choose the sliding surface. Sliding surface is equal to q plus k theta. So this is the sliding surface we are considering. And let us define this as equation number 2. Okay, so now I'm not going to detail about the how we can design the control, because what we can do is we have to take the time derivative of this equation 2, and from this we will substitute in q dot, we can substitute this equation, and in theta dot you can substitute this equation and we can find u, right, from that equation. And in place of s dot we can substitute the sigmoid function to make a chattering free in control. So the same steps what you have followed last lecture. After having all these mathematical steps analysis, the final control is found to be E equal to 1 upon AU minus KQ minus rho is divided by mod S plus epsilon minus A theta and minus AQ, AQ minus, sorry. So this is the overall control can be applied to the dynamics defined by equation 1 and which can stabilize the system. Here, after some iterations, the values of the control gain parameters after few iterations, the values of Kp, K rho and epsilon are considered as K equal to 1.5, rho equal to 2, and epsilon equal to 0.01. So if you remember in earlier lecture on sliding mode, this is basically we have used the sigmoid function, right? Why? Because to reduce the chattering in control. In the last lecture, we had signum function in control because we have the switching control and equivalent control, and switching control we have the signum function. But that control generally provides the chattering in the system. So to reduce the chattering, we came up the sigmoid function. So I request the learners, please do the mathematical analysis how we can find this u in this particular structure. Okay. So now we'll come to the MATLAB code, how we can make the system stabilized and chattering free. So this is the MATLAB code for this particular example. So if you notice here, uh, this is the initial values. This is the time period for the simulation. This is OD45 solver, and we have the function here, and we have the figures, and here we have this a theta, these values. We have whatever the values we have considered in the analysis we have taken here. This is basically your sliding surface and your control. This is the control what you have defined here. Okay. And if you notice here, the control input, you see is chattering free. There is no oscillations, sustained oscillation in the control. And also from the response of states, this is the response for Q, this is for theta, and you can see that over time it is finally stabilized to the system. And this is the sliding variable, what you have chosen here. So this is how we can design the control algorithm for this longitudinal motions. And if you have nonlinear longitudinal dynamics, you can proceed to the same steps. You have to find the error dynamics, and using error, you can find the sliding surface, and you can take the time derivative of the sliding surface, substitute the dynamics, and you can find the control from that. Okay. So now we are going to a new topic, which is backstepping sliding mode control. Okay. So I can use this part. Backstepping sliding mode control. This is a very important concept in the nonlinear control synthesis. Here we'll define the surface as well, and also we'll use that surface for the backstepping control concepts. Uh, as of now, we have covered the backstepping approach and sliding mode approach. Now we are going to combine them together to come up the robust controls. So here we are going to consider the same dynamics what we have taken before in this code lecture. So let us consider the dynamics, linearized model of the longitudinal motions. So here theta dot, the same expression q, and q dot equal to a theta theta plus a q q plus a u u, and we are also adding one term disturbance here. So here d is the disturbance. Also, we have taken in the previous example also in the disturbance. So if you notice here, this is the disturbance in the MATLAB code. This is the disturbance, right? So now we'll go step by step how we can design the control here. So step one, let us find the error. The error defined as. So if you notice here carefully, we have two equations. So, and if you notice the system is in recursive form, theta q is going to control theta and q is controlled by u, right? First, we'll take the first dynamics, theta dot equal to q, as you have done in the backstepping control. So here error can be defined as E equal to theta minus theta d zero. Okay. So here theta d zero be the desired trajectory. For pitch angle. It is for the time being, let us assume this desired trajectory to be the constant value, some constant. So we can better, if the desired values is constant, we can sometime you can call it tracking control, right? So let us define this, the equation number 1. This is 1 and this is 2. Okay. And differentiating equation 2, we get E dot equal to theta dot equal to Q. So here we assume theta desired to be constant value. So theta desired dot equal to 0. Now let's select the Lyapunov function. So we are trying to find the control for theta dot equal to Q, some virtual control you have to design for here. So as you have done in the backstepping control approach. So here, let us consider the Lyapunov function. Function as V1 equal to 1 upon 2 E square. Okay. And taking time derivative, V1 dot equal to E dot, or you can write E theta dot, or you can write E Q. And this is equation number 3. Okay. Now let us design the sliding surface in terms of U, because we have to change the state variable from actual to error form. So actual and desired to error variable. So we can define the sliding surface in terms of error. And here, let us now design sliding surface as S equal to E dot plus K1E. And here K1 is greater than 0. So if you notice at S equal to 0, this sliding surface is stable surface. It is asymptotically stable. So it is going to equilibrium point 0, because the equilibrium condition for this dynamics is 0, right? So now from this we can write E dot equal to S minus K1E. And here this E dot will substitute in equation 3. And let us define for equation 4, substituting the same step what you have done in the backstepping control design. Substitute equation 4 in equation 3, we can write V1 dot equal to E S minus K1. Okay, here we can write this is E dot here. So we are substituting here. Yeah. So K1 E, or we can write minus K1 E square plus ES. So it is very nice form that if S is equal to 0, we can say V1, this V1 dot is a negative definite. So we can say if you forgot the step in backstepping, please revisit again to understand this thing, because we are just simply following the same steps what you have done in the backstepping design process. So here, if S equal to 0, we get V1 dot equal to minus K1 E square, which is semi-definite, negative semi-definite. Hence, we can write here, hence, for the system to be stable, we need to we need to ensure S equal to 0. Now, what you're going to do is we'll take the second dynamics. Second dynamics into picture. For that, we need to redefine the Lyapunov function. So ensure this. We can write here. We do so by adding S in the Lyapunov function. Lyapunov function. So we can write V2 equal to V1 plus half S square. Now, if we take the time derivative of this expression, we can write V2 dot equal to V1 dot plus S dot. And V1 dot, in place of V1 dot, we can write minus K1 E squared plus ES. Already we have this expression, right? Now, for S, we can write as it is, S dot. And from this, we can write K1 E squared plus S E plus S dot. And let us define this equation number 5. And now we'll take the sliding surface to design controls. So sliding surface, this is the sliding surface. Okay, let me define this star. Now, taking the time derivative of equation star, we get S dot equal to Q dot plus Q1 E dot. And from this, Q dot already have, so we can substitute A theta theta plus A Q Q plus this is A and A U U plus disturbance plus K1 E dot, right? And what you can do is now S dot will substitute in equation 5. Now, this is 6, substituting equation 6 in equation 5, we have V2 dot equal to minus K1 square plus S into E plus A theta theta AQQ AUU plus disturbance plus K1 E dot. And if you choose, now we have to choose U in such a way that V2 dot is negative definite. So here we are choosing VU as we design U such that V2 dot is negative semi-definite. So U is chosen as 1 upon AU minus K2 is minus E minus A theta theta AQQ K1 E dot minus rho S divided by S plus epsilon. Yeah. So this is the overall control for the system defined by this equation 1 here, this equation. And this control is designed based on both sliding mode and backstepping. Now, if you substitute this U in equation, this is equation number 7. This is 8. Now substituting equation 8 in equation 7, we are having P2 dot is the minus K1 square minus K2 S square. So this is very simple. You can do it by yourself. This is not a difficult job. So from this, you can do P2 dot less than equal to 0. So we can say from this proof that hence we can write. So you can say E tends to 0 and S tends to 0 as T tends to infinity. So this is our control, equation 8. Now we'll see in simulation how the states being controlled. Okay. So this is the MATLAB simulation for this control. So here we can see that the pizza. Okay, these are the codes. You can please follow these codes. How you can try in your MATLAB command window. How this control can helps to stabilize the system. So here, this is basically the same function what you have taken before. So only the control part will change. And other than that, the things are almost same. So from this plot, it's clear that the pitch angle, this is a pitch angle, theta, which actually converts to 5 degree, right? So here we have the desired phi theta is, yeah, it is here 5 degree. So you can see that the pitch angle is converts to 5 degree in finite time, and states are approximately converts to the sliding surface as s tends to s goes to 0, right? So also we can see that this control is highly robust because even in the presence of disturbance, the system is getting stabilized and reaching to the desired values in finite time. This is how we can design the sliding mode control for linear or nonlinear system. And if you need to design the same control techniques, the sliding mode control or combined sliding mode and backstepping for your system, so you can use this MATLAB code help, and you can come up your own autopilot and control design algorithms for the different subsystems or different systems. If it is robotic or aircraft, missile, you can easily do it. So let's stop it here. From next lecture onwards, we'll be coming up new topic, adaptive control, and how we can design adaptive control for the aircraft system. Then we'll wind up this control part. Thank you.